The intent of NEC 250.50 regarding concrete encased electrodes is often debated, especially concerning the minimum requirements for grounding. This discussion clarifies several key interpretations related to this section of the National Electrical Code, specifically focusing on situations encountered in areas like the Texas Gulf Coast. The first question addresses whether 250.50 requires a minimum of 20 feet of 1/2 inch or greater diameter rebar in the footer if the concrete slab itself doesn't contain this amount of steel. The intent is yes. If the concrete slab lacks 20 feet or more of 1/2 inch or greater diameter rebar, then the code's intent is to require this amount of steel in the footer to serve as the grounding electrode. This ensures a sufficient connection to earth for grounding purposes. The second question explores the impact of a plastic vapor barrier between the slab and the earth on the interpretation of 250.50. The vapor barrier's presence can affect the interpretation because it introduces an insulating layer between the concrete and the earth. This barrier reduces the direct contact between the concrete and the ground, which in turn diminishes the effectiveness of the concrete slab as a grounding electrode. Therefore, a vapor barrier might necessitate additional grounding measures to compensate for the reduced conductivity. The third question asks whether the code permits or requires, in lieu of the specified rebar, 20 feet or more of bare copper not smaller than 4 AWG. The code does not require bare copper in lieu of the rebar. However, it permits the use of bare copper not smaller than 4 AWG as a grounding electrode in other circumstances, such as for grounding service equipment. This means that while copper can be used as a grounding electrode, it's not a mandatory substitute for the rebar within the concrete slab. The fourth question concerns pre-stressed post-tension slabs with plastic-coated reinforcing steel, asking if the intent is to require 20 feet of 1/2 inch rebar or greater, or 20 feet of 4 AWG copper in such slabs. The intent of the code is to require either 20 feet of 1/2 inch rebar or greater, or 20 feet of 4 AWG copper, even if the reinforcing steel is plastic coated. The plastic coating is generally considered not to significantly impede the conductivity of the steel for grounding purposes. Therefore, the presence of the coating does not negate the requirement for the specified amount of rebar or copper. In summary, understanding the specific requirements and interpretations of 250.50 is crucial for ensuring proper grounding in construction. The presence of a vapor barrier, the type of concrete slab, and the use of rebar versus copper all play a role in determining the appropriate grounding measures. Always refer to the latest edition of the National Electrical Code and consult with qualified electrical professionals for specific applications. It's important to note that the NEC guidelines are designed to ensure safety and proper electrical grounding, which is fundamental to preventing electrical hazards and ensuring the reliable operation of electrical systems. The minimum requirements outlined in 250.50 serve as a baseline, and additional measures may be necessary depending on local conditions and specific project requirements. To elaborate further on the role of concrete encased electrodes, often referred to as UFA grounds, these grounding electrodes are highly effective due to the large surface area of contact with the earth. This large surface area provides a low impedance path for fault current to return to the source, thereby facilitating the quick operation of overcurrent protective devices like circuit breakers and fuses. The 20-foot requirement for rebar within the concrete is based on empirical data and testing that has demonstrated the effectiveness of this length in providing adequate grounding in most soil conditions. The diameter of the rebar, 1/2 inch or greater, is also important because it ensures sufficient cross-sectional area for conducting fault current. Regarding the vapor barrier, it's critical to consider its impact on the overall grounding system. While the code doesn't explicitly prohibit the use of vapor barriers, their presence necessitates careful evaluation of the grounding system's effectiveness. If a vapor barrier significantly reduces the contact between the concrete and the earth, supplementary grounding electrodes may be required to meet the code's intent. These supplementary electrodes could include ground rods, ground plates, or other approved grounding methods. When using bare copper wire as a grounding electrode, it's essential to ensure that it is properly installed and protected from physical damage. The wire should be buried directly in the earth and should be free from sharp bends or kinks that could compromise its conductivity. The 4 AWG size requirement is based on the wire's ability to carry the anticipated fault current without overheating or becoming damaged. In the case of pre-stressed post-tension slabs, the plastic coating on the reinforcing steel is typically thin and doesn't significantly impede the flow of current. However, it's still important to verify the conductivity of the steel and ensure that the grounding electrode is properly connected to the reinforcing steel. This can be achieved by using approved bonding methods and connectors. Furthermore, it's worth noting that the NEC allows for alternative grounding electrode systems if they can be demonstrated to be as effective as the concrete encased electrode. These alternative systems may include engineered grounding systems or other methods that provide a low impedance path to earth. However, any alternative system must be approved by the local authority having jurisdiction. In addition to the physical requirements for grounding electrodes, it's also important to consider the electrical characteristics of the soil. Soil resistivity can vary significantly depending on factors such as moisture content, temperature, and chemical composition. High soil resistivity can increase the impedance of the grounding system, which can reduce its effectiveness. In areas with high soil resistivity, it may be necessary to use multiple grounding electrodes or to treat the soil to reduce its resistivity. Proper grounding is not only essential for safety, but also for the proper functioning of sensitive electronic equipment. Electronic devices are susceptible to damage from voltage surges and electrical noise, which can be mitigated by a properly designed and installed grounding system. A well-grounded system provides a stable reference point for voltage, which helps to reduce noise and prevent damage to sensitive equipment. Regular inspection and testing of grounding systems are also crucial to ensure their continued effectiveness. Grounding electrodes can corrode over time, which can increase their impedance and reduce their ability to carry fault current. It's recommended to periodically inspect grounding electrodes for signs of corrosion and to test their impedance to ensure that they meet the code requirements. The testing of grounding systems typically involves using a ground resistance meter, which measures the resistance between the grounding electrode and the earth. The measured resistance should be below a certain threshold, as specified by the NEC, to ensure that the grounding system is effective. In conclusion, NEC 250.50 provides specific guidelines for the installation of concrete encased electrodes, but the interpretation and application of these guidelines can be complex. Factors such as the presence of vapor barriers, the type of concrete slab, and the use of rebar versus copper all play a role in determining the appropriate grounding measures. Proper grounding is essential for safety and the proper functioning of electrical systems, and it's important to consult with qualified electrical professionals to ensure that grounding systems are designed and installed in accordance with the code. In addition to the points already discussed, it's crucial to understand the concept of bonding in relation to grounding. Bonding refers to the practice of connecting all metallic parts of an electrical system together to create a common electrical potential. This includes items such as metal conduits, metal enclosures, and metal water pipes. Bonding helps to reduce the risk of electric shock by ensuring that there are no voltage differences between these metallic parts. The NEC requires that all metallic parts of an electrical system be bonded together, and that the bonding system be connected to the grounding electrode. This creates a low impedance path for fault current to return to the source, which helps to ensure the quick operation of overcurrent protective devices. There are several different methods for bonding metallic parts, including using bonding jumpers, bonding bushings, and grounding clamps. The specific method used will depend on the type of metallic part being bonded and the requirements of the NEC. It's important to use approved bonding methods and connectors to ensure that the bonding system is effective. Another important aspect of grounding is the size of the grounding electrode conductor. The grounding electrode conductor is the wire that connects the grounding electrode to the electrical system. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. The NEC provides tables that specify the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. It's important to use the correct size grounding electrode conductor to ensure that it can carry the anticipated fault current without overheating or becoming damaged. In addition to the grounding electrode conductor, it's also important to consider the size of the equipment grounding conductor. The equipment grounding conductor is the wire that connects the metallic parts of electrical equipment to the grounding system. The size of the equipment grounding conductor is determined by the size of the overcurrent protective device protecting the circuit. The NEC provides tables that specify the minimum size of the equipment grounding conductor based on the size of the overcurrent protective device. It's important to use the correct size equipment grounding conductor to ensure that it can carry the anticipated fault current without overheating or becoming damaged. Furthermore, it's worth mentioning the importance of proper labeling and documentation of grounding systems. All grounding electrodes and grounding electrode conductors should be clearly labeled to indicate their purpose. This helps to prevent confusion and ensures that the grounding system is properly maintained. Documentation of the grounding system should include details such as the location of grounding electrodes, the size of grounding electrode conductors, and the methods used for bonding metallic parts. This documentation should be kept readily available for future reference. In addition to the NEC requirements, there may be local codes or regulations that govern the installation of grounding systems. It's important to check with the local authority having jurisdiction to ensure that the grounding system complies with all applicable codes and regulations. Finally, it's important to remember that grounding is a complex and critical aspect of electrical safety. It's always best to consult with qualified electrical professionals to ensure that grounding systems are designed and installed properly. Attempting to install or modify a grounding system without the necessary knowledge and experience can be dangerous and can result in serious injury or property damage. In the context of the questions posed, understanding the nuances of 250.50 is paramount. Firstly, the emphasis on 20 feet of rebar serves as a baseline for effective grounding within a concrete structure. This length is not arbitrary. It's rooted in the principle of maximizing contact with the earth to facilitate the dissipation of fault currents. When a structure lacks this inherent grounding capability due to insufficient rebar in the slab, the code mandates the inclusion of the specified amount in the footer to compensate. Secondly, the presence of a vapor barrier introduces a layer of insulation between the concrete and the earth, impeding the direct flow of current. This necessitates a reassessment of the grounding strategy to ensure that the system remains effective despite the barrier's presence. Supplementary measures may be required to bridge the gap created by the vapor barrier and maintain a reliable connection to ground. Thirdly, while copper can indeed serve as an alternative grounding electrode under certain circumstances, it is not a direct substitute for the rebar specified within the concrete slab. The code distinguishes between the two, recognizing the unique role of rebar in providing grounding within the concrete structure itself. Copper electrodes are typically employed for grounding service equipment or other specific applications, rather than as a replacement for the rebar embedded within the concrete. Fourthly, the presence of a plastic coating on the reinforcing steel does not negate the need for grounding. While the coating may introduce a slight impedance, it is generally considered negligible in the context of grounding. The intent of the code remains to ensure that the reinforcing steel is properly grounded, regardless of the presence of the coating. This underscores the importance of adhering to the specified grounding requirements, even in situations where the reinforcing steel is coated. In essence, the interpretation of 250.50 hinges on a thorough understanding of the underlying principles of grounding, as well as the specific characteristics of the construction materials and site conditions. Consulting with qualified electrical professionals and adhering to the latest edition of the National Electrical Code are essential steps in ensuring compliance and maintaining a safe and reliable electrical system. Let's consider additional scenarios that might arise in the context of 250.50. What if the concrete slab is not in direct contact with the earth, but is elevated above ground level? In such cases, the concrete slab cannot be considered a grounding electrode, as it lacks the necessary contact with the earth. Alternative grounding methods, such as ground rods or ground plates, would be required to provide a path to ground. What if the soil surrounding the concrete slab is highly corrosive? In such cases, the grounding electrode may be subject to accelerated corrosion, which can compromise its effectiveness. It may be necessary to use corrosion-resistant materials or to provide additional protection to the grounding electrode to prevent corrosion. What if the concrete slab is part of a larger structure that includes other grounding electrodes, such as a metal water pipe or a building steel? In such cases, it's important to ensure that all grounding electrodes are properly bonded together to create a common grounding system. This helps to prevent voltage differences between the different grounding electrodes and ensures that fault currents are properly dissipated. What if the concrete slab is located in an area with high levels of lightning activity? In such cases, it may be necessary to provide additional lightning protection measures such as lightning rods or surge arresters to protect the electrical system from damage due to lightning strikes. What if the concrete slab is part of a swimming pool or other wet location? In such cases, it's important to follow the specific grounding requirements for wet locations as outlined in the NEC. These requirements are designed to minimize the risk of electric shock in wet environments. What if the concrete slab is part of a modular building or prefabricated structure? In such cases, it's important to ensure that the grounding system is properly installed and connected to the building's grounding system. This may require special considerations, depending on the design of the modular building or prefabricated structure. What if the concrete slab is located in an area with limited access? In such cases, it may be necessary to use specialized equipment or techniques to install the grounding electrode. This may require careful planning and coordination to ensure that the grounding electrode is properly installed. What if the concrete slab is part of a historical building or landmark? In such cases, it's important to consider the historical significance of the building and to minimize any impact on its historical integrity. This may require careful planning and consultation with historical preservation experts. What if the concrete slab is part of a green building or sustainable design project? In such cases, it's important to consider the environmental impact of the grounding system and to use sustainable materials and practices whenever possible. This may involve using recycled materials or implementing energy-efficient grounding techniques. In all of these scenarios, it's important to consult with qualified electrical professionals and to adhere to the latest edition of the National Electrical Code to ensure that the grounding system is designed and installed properly. Grounding is a critical aspect of electrical safety, and it's essential to take all necessary precautions to protect people and property from electrical hazards. To further clarify, consider the practical implications of these code requirements for home builders in the Texas Gulf Coast. This region is known for its challenging soil conditions, including high moisture content and corrosive soils, which can significantly impact the effectiveness and longevity of grounding systems. Therefore, home builders in this area must be particularly diligent in their approach to grounding, taking into account the specific conditions of each site. Firstly, when pouring concrete slabs, builders must ensure that the specified amount of rebar, either 20 feet of 1/2 inch or greater diameter, is properly embedded within the concrete. This requires careful planning and execution during the construction process to ensure that the rebar is correctly positioned and secured. Secondly, builders must be aware of the potential impact of vapor barriers on the grounding system. If a vapor barrier is used, they must take steps to mitigate its effects, such as by installing supplementary grounding electrodes or by using a vapor barrier material that is specifically designed to allow for electrical conductivity. Thirdly, builders must ensure that all grounding electrodes, including concrete encased electrodes, ground rods, and ground plates, are properly bonded together to create a common grounding system. This requires the use of approved bonding methods and connectors to ensure that the connections are secure and reliable. Fourthly, builders must be aware of the potential for corrosion in the soil and take steps to protect the grounding electrodes from corrosion. This may involve using corrosion-resistant materials or by applying a protective coating to the grounding electrodes. Fifthly, builders must ensure that the grounding system is properly inspected and tested before the building is occupied. This requires the use of a ground resistance meter to measure the resistance between the grounding electrode and the earth. The measured resistance should be below a certain threshold, as specified by the NEC, to ensure that the grounding system is effective. In addition to these practical considerations, home builders in the Texas Gulf Coast must also be aware of any local codes or regulations that may govern the installation of grounding systems. It's important to check with the local authority having jurisdiction to ensure that the grounding system complies with all applicable codes and regulations. By following these guidelines and taking into account the specific conditions of the Texas Gulf Coast, home builders can ensure that their homes are properly grounded and that their residents are protected from electrical hazards. Grounding is a critical aspect of electrical safety, and it's essential to take all necessary precautions to ensure that it is done correctly. It's also important to emphasize the ongoing maintenance and inspection requirements for grounding systems. Over time, grounding electrodes can corrode or become damaged, which can compromise their effectiveness. Therefore, it's recommended that grounding systems be periodically inspected and tested to ensure that they are functioning properly. The frequency of these inspections will depend on the specific conditions of the site, but it's generally recommended to inspect grounding systems at least every 3 years. During these inspections, the grounding electrodes should be visually inspected for signs of corrosion or damage. The connections between the grounding electrodes and the grounding electrode conductor should also be inspected to ensure that they are secure and reliable. In addition to visual inspections, the grounding system should also be tested using a ground resistance meter to measure the resistance between the grounding electrode and the earth. If the measured resistance is above the specified threshold, the grounding system should be repaired or replaced as necessary. It's also important to keep accurate records of all grounding system inspections and tests. These records should include the date of the inspection, the results of the tests, and any repairs or replacements that were made. This documentation can be useful for tracking the performance of the grounding system over time and for identifying any potential problems. In conclusion, NEC 250.50 provides specific guidelines for the installation of concrete encased electrodes, but the interpretation and application of these guidelines can be complex. Factors such as the presence of vapor barriers, the type of concrete slab, and the use of rebar versus copper all play a role in determining the appropriate grounding measures. Proper grounding is essential for safety and the proper functioning of electrical systems, and it's important to consult with qualified electrical professionals to ensure that grounding systems are designed, installed, and maintained in accordance with the code.